In this lesson, we will be looking at half-life, and we're going to be starting with some review of some key terms. So you should remember that an alpha particle is really a helium nucleus, meaning that it has 2 protons and 2 neutrons. The symbol for alpha is like this, and we could also write an alpha particle as a mass of 4, 2 for the atomic number, and the symbol for helium. An alpha particle has relatively low energy, and an alpha particle has a positive charge. Next, we have a beta particle, and this is the symbol for beta. A beta particle is a high energy electron. And therefore a beta particle has a negative charge. Could also write a beta particle as an E for electron, mass of 0, and -1. Next we have gamma rays, and gamma rays are really high energy electromagnetic radiation. So they're high energy radiation. Symbol for gamma is like this, or we could say like this. Gamma rays have no mass, and they also have no charge. I'm also going to introduce you to the term neutrino. And a neutrino is a subatomic particle containing only energy. And it also has no mass and no charge. The degree of radioactivity is measured in becquerels, and becquerels is abbreviated BQ. So we can define this as the unit that is used to measure how radioactive something is, so the degree of radioactivity. And it's measured in decays per second. So measured as decays per second. We're going to start looking at decay series. So a decay series is when a radioactive parent nucleus decays to form an unstable daughter nucleus. And because the daughter nucleus is not stable, it's also going to decay. And this is going to continue until a stable daughter is produced. So for example, we could have uranium-238. So say uranium-238. And it can undergo alpha decay to produce thorium-234. Which is also unstable. It can undergo beta decay to produce protactinium, so that's Pa 234. Beta decay. This could undergo another beta decay to produce uranium again, 234, which can undergo alpha decay to produce thorium, which is 230, which in turn can undergo an alpha decay to produce radium, 226, which can undergo, I'll stop writing this out, an alpha decay and then another beta decay to produce lead, 206. This is stable, so the decay series will stop here. The actual rate of decay is not affected by physical or chemical changes, and the age of the nucleus does not affect the probability that it will decay. We can't predict when any one given nucleus is going to decay, but we can predict the average rate of decay for a large number of nuclei. The number of decays per second of a sample is known as the activity of the sample. And we measure the activity in decays per second, so we measure it in becquerels. Symbol for becquerels is BQ. And 1 becquerel, so 1 BQ equals 1 decay per second. So the activity of the sample is going to depend on the size of the sample. Now this brings us to half-life. Half-life is the average length of time that it takes for half of the parent nuclei in a sample to decay. So it's the average length of time for half of the parent nuclei in a sample to decay. This is different for each isotope, but it's constant for a given isotope. And we'll look at a couple of graphs to see the pattern that all radioactivities follow. So scrolling down, here we'll just look at one. So we started here with 100 parent nuclei. So the half-life is the average length of time for half of them to decay. So we have to go down to when we have half, and that's here when we have 50. And then you can go over and read, and this is going down to the time, 5. So that's probably 5 minutes. If we have 50 after 5 minutes, then after another 5 minutes, it will half again. So at 10 minutes, we now have 25, and so on. And this is called a decay curve. A decay curve is a graph of the mass of the radioactive isotope over time. So a graph of the mass of a radioactive isotope over time. We're going to stop here and in class practice working with decay curves, and we will look at the sample problems next day.